welcome to Math 120, lecture for section 5.3 from home. So we're going to be looking at a handout from section 5.3, and the first page of the handout gives you a 7-step process for analyzing the graph of a rational function. If you haven't read through those 7 steps yet, go ahead and pause the video at this point and read through those 7 steps. Now that you've read through those 7 steps, let's go ahead and check out example 1 on page 2. So as you look at example 1, the first statement is that the directions say, analyze the graph. Sometimes when people read those words, they're not quite certain what that means. Analyze the graph means we're going to tear apart this function and see what all the interesting things are about that function, and then we're going to interpret those ideas as a graph. So anytime the author uses the phrase analyze the graph, he's really wanting us at the end of the problem to have a graph drawn. So let's figure out how to make this happen. So first off then, you're going to notice on the handout I have a big horizontal bar, I would say about 1/3 of the way down the page. And this goes back to something we talked about in section 5.2, that certain things have to happen before you cancel common factors, and certain things have to happen after you cancel those common factors. So you'll notice the bar is right underneath domain. You need to make sure that you find your domain before you cancel your common factors, and everything else happens after you cancel your common factors. So you want to keep that in mind as we move forward through these problems. So let's go ahead and take them one at a time. So the first item on your handout says factored form of f. Well, in this particular problem, I already gave it to you in factored form, so we're done with that. And then we have a spot for the domain. Well, remember from things we talked about earlier in the course, the domain has to have then 2 things that you ask about. First off, are we going to be dividing by any x's? And definitely when we're looking at a rational function, we will be. So when you look at this problem, you have to ask yourself, what x values would make any of our denominator factors 0? Well, if we have a factor of x minus 3, that means then that we're going to have a 0 of 3 associated with that. That means that 3 would zero out that factor, it would make the denominator 0, and we can't divide by 0. So we can't play with 3. So for our domain, we're going to have the set of all x values such that, and you want to say, I don't like 3. And then similarly, as you look at that factor of x plus 5, if the factor is x plus 5, negative 5 is the 0 associated with it, that would make our denominator 0, and we can't play with that either. So the domain, in set builder notation, is the set of all x values such that x is not equal to 3, x is not equal to negative 5. Now, the next piece then on your handout says that we should go ahead and cancel any common factors. In this particular problem, you're going to notice we have a factor of x plus 1, factor of x minus 3, and a factor of x plus 5. Nothing is common to the numerator and to the denominator, so that means then that we're not going to be able to do any cancellation on this problem. So we'll move on to y-intercept. As you see on your handout, in order to do the y-intercept, it's the same thing we've done every other time for y-intercepts. You replace x by 0. So I'm going to find f of 0. So I'll go back up to my original function. Wherever I see an x, I'm going to replace that x by 0. So it's going to be 0 plus 1 divided by 0 minus 3 quantity squared times 0 plus 5. Well, 0 plus 1 is 1, and then 0 minus 3 is a negative 3. If I square that, I'm going to have 9. And then 0 plus 5 is 5. So that means then that I have 1 divided by 9 times 5. 9 times 5 is 45. So this is 1 divided by 45. So now that I know my y-intercept is 1 divided by 45, I can actually go to my Cartesian coordinate system and start plotting some of that information. So let's go to the Cartesian coordinate system. 1 over 45 is a small fraction close to 0, and it's positive. So we can come in here and put a dot right there, slightly above 0 on the y-axis. Well, let's keep going. Next off, x-intercepts. Well, an x-intercept is something that's going to make your y value 0. Well, the only way that you can make a fraction 0 is if the numerator is 0. So whenever you're looking at an x-intercept, for a rational function, what you're really doing is finding the zeros of the numerator. Well, our factor is x plus 1, so the 0 that goes with that is negative 1. So our x-intercept is negative 1. Now, once we know that our x-intercept is negative 1, we can also take some of the information we learned about in terms of polynomials and have a sense of what the behavior of this graph is going to be near that x-intercept of negative 1. So notice this x plus 1 is to the first power. So that means that the multiplicity of our 0 is odd. If the multiplicity is odd, that means that we're going to have a crossing behavior near that x-intercept of negative 1. So let's go ahead and plot negative 1 as an x-intercept, and keep in mind that we're going to have that crossing behavior there. Well, let's keep going. Next off then, vertical asymptotes. First off, remember that your author will always simply say, what's the vertical asymptote? But he's always asking you to write down the equation of that vertical asymptote. So anytime you write down a vertical asymptote, make sure you start off with x equals. And then secondly, remember the vertical asymptotes come from zeros of the denominator. So once again, we have x minus 3 to the second power in the denominator. X minus 3, that's the factor. The 0 that goes with that is positive 3. So one of our vertical asymptotes will be x equals 3. Our other factor in the denominator is x plus 5. The 0 associated with that would be a negative 5. So our other vertical asymptote is x equals negative 5. So now that we have those two pieces of information, let's go ahead and put those on our graph as well. X equals 3 is a vertical asymptote. And what we saw in section 5.2 is that a vertical asymptote is a dashed vertical line that our graph is going to approach. So, okay, let's go to x equals 3 and put a dashed vertical line there. And similarly, we're going to have a dashed vertical line at x equals negative 5. So we'll come over here to negative 5 and write that down. Now, in order to figure out what's happening in terms of behavior near the vertical asymptote, I've written some information on your handout. So if you haven't read that, go ahead and pause the video for a moment and read that information. So now that you've read that then, let's go back to this x minus 3. Notice x minus 3 is to the second power. So that means then that the 0 of 3 has an even multiplicity. Based on what you just read, if you have an even multiplicity for a 0 associated with a vertical asymptote, that means then that both sides are going to have the same behavior. So when you go over here to x equals 3, both sides are going to go up near that vertical asymptote, or both sides are going to go down near that vertical asymptote. However, on the other side, x equals negative 5, that has a power of 1, so the multiplicity of negative 5 is odd. If you have an odd multiplicity, the two sides behave differently. On one side you're going to go up, and on the other side you're going to go down. So we want to keep that in mind as we move forward as well. Next off then, let's figure out whether we have a horizontal or an oblique asymptote. This once again goes back to some of the things we talked about in section 5.2. So you might need to pull out your handout from section 5.2 and check out that table that talked about horizontal and oblique asymptotes. So horizontal and oblique asymptotes all come down to figuring out whether you have the degree of the numerator being the same as the degree of the denominator, the degree of the numerator being less than the degree of the denominator, or the degree of the numerator being greater than the degree of the denominator by 1. So let's figure out our degrees and then figure out whether we have a horizontal or an oblique asymptote. So x plus 1 to the first power. That means that our numerator has a power of 1. And then we have x minus 3 squared and x plus 5 to the first in the denominator. So we're going to have an x squared and an x to the first. X squared times x to the first is x to the third. So we're going to have a power of 3 in the denominator. So in this case, the degree of the numerator is less than the degree of the denominator. So the first thing you should have from section 5.2 is that if the degree of the numerator is less than the degree of the denominator, you're going to have a horizontal asymptote. So we'll come down here to oblique and say none. And And then the second thing that you should have from section 5.2 is that if the degree of the numerator is less than the degree of the denominator, the equation for that horizontal asymptote is y equals 0. Well, once again, the horizontal asymptote is a dashed horizontal line that our graph approaches way out to the left and way out to the right. So let's go ahead and put a dashed horizontal line for y equals 0. And once again, y equals 0 is the x-axis. Now, at this point, we truly do have enough information that we could graph this graph. However, it's nice to be able to create something called a sign chart to give us just a little bit more information about how this graph comes together. And what I'm going to do is pause the video, erase, and then do a sign chart for you.